So here we are on alcohol's video part 2, and this is the probably the most important part of this section in what can happen to form an alcohol. So we can draw one resonance structure for acetone, and since the oxygen is more electronegative than the carbon, we know when this pi bond breaks, it's going to send the electrons up to the oxygen to give it another lone pair. So our one resonance structure has an oxygen with 3 lone pairs. It has to have a negative charge then, because it has more electrons assigned to it, and since we have a negative, we have to have a positive somewhere. The carbon lost a bond to it, so it ends up with a positive charge. So the one resonance structure for a carbonyl is sending the electrons up to the oxygen, giving us a negative on the oxygen and a positive on the carbon. The hybridization of that central carbon is sp2 with a 120 degree bond angle. Not that we asked for that, but it's sp2 because it has 3 things around it. Single bonds, double bonds, triple bonds, and lone pairs all count as 1 when we're figuring out the hybridization. So it's got 3 things. It's got to be sp2 hybridized. The nucleophile, any nucleophile, where's it going to add? It's going to add to the carbonyl carbon, because that's where we have the positive charge in the resonance structure, or in the structure we have a partial positive there. So if we were to draw a mechanism for this, the nucleophile would add to the carbon, sending the electrons up to the oxygen, and our product would look like this. And it doesn't matter what the nucleophile is, they're all going to do the same sort of thing. Okay. Now, for which of the molecules lowest oxidation state, all we're looking for is the easy part of this, and the more oxidized something is, the more oxygens are on it. So this is going to be 1, the alkane, the alcohol is going to be 2, the aldehyde or ketone carbonyl is 3, and the acid is 4 for the most oxidized of the 4. Whoops. So organometallic compounds, we know the charge on this is lithium metal. It has no charge. When lithium metal reacts, it forms lithium with a +1. So if we form this alkyl lithium and a lithium bromide around, we know, well, we'll get to the charge in a second. And the second one, the magnesium, when magnesium reacts, it forms a magnesium +2. So it needs 2 things connected to it. So it's going to have to insert basically in between the carbon and the bromine. And we're going to form the alkyl magnesium bromide in this case. So if we draw the alkyl lithium, we know the lithium has a +1. And so if the lithium has a +1, this carbon that it is connected to has to have a -1 on it. And the same with the alkyl magnesium bromide. If we forget about the bond between the two and just think about the atoms, the magnesium has a +2, the bromine has a -1, so this MgBr has to have a +1 for the whole ion, basically. So if it's +1, the carbon has to be a -1. We also know that between carbon and lithium, or carbon and magnesium, when we go through the mnemonic in the syllabus for outdoor clam bakes, never bring canned salmon, ham, or pancakes, okay, carbon is more electronegative than any of the metals, so it's going to have the more electron density on it with a positive on the metal. Okay, that's just a simple basic from Gen Chem. So if we draw just the alkyl anion, okay, and it's not completely an ionic bond, but for drawing the mechanism, it's much easier to ignore the magnesium bromide and just put the negative with a lone pair on the carbon and see what it can do. It adds to the carbonyl, sending the electrons up to the oxygen, and we get this with the alkoxide. Okay, we have to make sure when we form the bond between the carbon and the carbonyl that we don't leave it there, because that would be 5 bonds to that poor little carbon, and we all know carbon can't have 5 bonds. So what can happen if we add an alkyl anion to all of these things? If we add it to water, we know water has an acidic hydrogen, so this is just going to give us propane and hydroxide. So if we have any water around in our Grignard reaction, we're going to completely kill off the Grignard reagent and just get hydroxide out of it, which is not what we want to do. In methanol, we know the most acidic hydrogen is the hydrogen on the oxygen, so again, we're going to get propane, but the side product would be methoxide. And again, this isn't something we would want to do because we're using a alkyl lithium, a compound that's hard, it takes a lot of work to come up with to make methoxide. There are much easier ways if we wanted to make methoxide to make methoxide. And the last one here, the methylacetylene, we know the pKa for the acetylenic hydrogen is about 25. The pKa for just an regular sp3 hydrogen is about 50, so the hydrogen that we're going to remove is the acetylenic hydrogen to form propane along with the methylacetylide ion. Okay, so we're going to take off the most acidic hydrogen. We know the pKa for any of these hydrogens in propane is about 50. So between propane and methylacetylene, this equilibrium lies very strongly to the right, because in an acid-base reaction, we always go to the weaker acid and weaker base. So if we were to draw the mechanism between the alkyl lithium reacting with water, we know the alkyl lithium is going to grab a hydrogen, and the bond between the H and the O breaks, sending the electrons to the oxygen based on electronegativity of that bond to give us the propane along with hydroxide. Okay. Now, down at the bottom, we have 2 reactions that we're asked to predict the products for. Thinking back to Org 1, if we ignore the magnesium bromide, just have a negative on that carbon, the ethyl anion is a strong base, strong nucleophile. This is going to be basically an SN2 mechanism, and in an SN2 mechanism, the strong nucleophile adds to the least substituted carbon. So the methyl anion is going to add here, breaking the bond to the oxygen, sending the electrons up to the oxygen, giving us a 5-carbon chain with our oxygen on the second carbon in there. The bond we formed, you draw it in blue, is this bond right here between the 2 carbons that were the ethyl group, that's these 2, and the 3 carbons that were the epoxide, those 2. Okay. Then the next one, methyl magnesium bromide and acetone, is just going to get followed by acid, In all of these, we reacted with acid in the second step, so we need to get to the neutral alcohol. But we're going to get to tertiary alcohol in the last one. So here, can you draw a mechanism for methyl magnesium bromide, the methyl anion, reacting with an ester? The first thing that's going to happen is we add it in, break the double bond. That gives us the tetrahedral intermediate, the O minus, with an OCH3. The O minus can reform a carbonyl, kicking out the methoxide to give us a carbonyl, and then this, another equivalent of methyl magnesium bromide, can add to the acetone to give us the tertiary alcohol. So an ester can add a Grignard twice because of this OCH3. That OCH3 is what we have talked about all along as a good what? Think about it for a second. I'll give you a break. What can you say about that OCH3? You're right, it is a good leaving group. So, because we can form the carbon-oxygen double bond, which is more stable than two single-bonded oxygen bonds. So that's why we can add 2 about that to the ester, is because we have that leaving group on there. Okay, now for alcohols, if we have an alcohol and a alkyl halide in the same molecule, we cannot, based on what we just talked about, make the Grignard with the alcohol in the reaction, because the Grignard, if we could form the Grignard, this O- would immediately take the hydrogen off of the alcohol. Now, if you have an alcohol in the molecule, you can't make the Grignard at all. It doesn't work because the Grignard is not stable and all of that. So what we have to do is protect the alcohol, and there are ways we can protect the alcohol. The easiest one is with a silyl compound. TMSCl is one of the good ones, but it doesn't matter what it is as long as we have a good leaving group on the silicon, in this case the chloride. It could be could be other leaving groups. There's you could put a mesylate or a triflate on it also. So, but the silyl chloride is a good choice. So TMSCl, trimethyl silyl chloride, makes the TMS ether. The TMS ether doesn't have an acidic hydrogen on it, so we can make the Grignard with magnesium, add a carbonyl to it, in this case formaldehyde, so we add 1 carbon, and then we can cleave the TMS, the silicon ether, with tetrabutyl ammonium fluoride. And what am I doing? And in this, the fluoride silicon bond that is formed when the fluoride attacks the silicon, kicking out the oxygen, basically, that silicon fluoride bond is so strong, it is stronger than the bond of the oxygen. So that is why it attacks the silicon, kicking out the oxygen to make the alcohol. Okay, so tetrabutyl ammonium fluoride, TBAF, is one of the main ways you can use to cleave that TMS or any silicon group off. So we remember SN1 reactions from Org 1. Okay, if we were to draw the mechanism for this, we know the alcohol is going to go grab a hydrogen off of the strong acid to make the protonated alcohol, because an OH is not a good leaving group, but an OH2 plus is a good leaving group, so we can form the cation, and then to that cation we can add our nucleophile in to form the product. Now we know in an SN1 we need a weak base, weak nucleophile. We need a tertiary leaving group is best. Okay, if we don't have a good leaving group, we have to be able to make a good leaving group, like in this case. But with a weak base, weak nucleophile, and a tertiary leaving group, it's easiest to form a carbocation. and with the tertiary compounds, the carbocation is more stable, so it's easier to form, so that's why it goes through the SN1. Okay. In an SN2 mechanism shown on the bottom of the page, if we don't have a good leaving group, we have to make one. So we have to 1, 2, 3, 4 protonate the alcohol, make the OH2 plus, and then the Br minus can come in and displace it directly to give us the alkyl bromide. In an SN2, a primary leaving group works best, and works best with a good nucleophile and a good leaving group, but in this case we can do it with HBr in that we make the good leaving group and then do something with it. Okay. A second way to convert an alcohol into a good leaving group is to make a tosylate. Okay. Now, the alcohol, as we said, is a bad leaving group, but if we had tosyl chloride and pyridine, we make the tosylate. The tosylate is a really good nucleophile. If we have stereochemistry, we have to be careful of what happens in that stereochemistry, but the nucleophile in an SN2 comes in from the back side to displace the good leaving group to give us our product. So in this case, our alcohol is S because the highest priority group is the alcohol. The ethyl is 2, the methyl is 3, the hydrogen in back is 4, it's in back, it doesn't matter. So that the arrow from 1 to 2 to 3 goes counterclockwise, so it is S. So after making the tosylate, nothing changed about the stereochemistry because we changed the oxygen-hydrogen bond, not the oxygen-carbon bond. So we didn't do anything to the bond that has the stereocenter. We just put the tosylate on there. And then in the step with the nucleophile, then we broke the bond between the carbon and the leaving group, changing the stereochemistry. So now the nucleophile is going back, the hydrogen is coming forward. We need to either be able to recognize that 2 of the groups were flipped and 2 are the same, so we know it has to be the mirror image of the structure, the stereocenter we started with, or we have to be able to redraw this with the hydrogen in back, showing that it is R in our mind, that we wrote down the correct answer. Okay. The third way we can do about this is either with PBr3, phosphorus tribromide, or thionyl chloride, and these both undergo an SN2 type process in the mechanism, so they work best on primary alcohols. They replace the alcohol with the halogen, and now we've turned the alcohol, which was a bad leaving group, into a good leaving group. So the mechanism for the reaction with thionyl chloride, the oxygen goes and attacks the sulfur. We break the SO double bond. Anytime we have a double bond, we need to, and we add a nucleophile to it, we need to break the double bond, forming the tetrahedral intermediate, and then do something else. Do not do the direct displacement on the chloride leaving group when you have a double bond there. Oh, take points off. You have to add it in and then reform it. Now, once we've done that, there are 2 things that can happen, and we could draw it in either order. This mechanism, we have the pyridine come grab the extra hydrogen off of our oxygen to get to the neutral or the negatively charged compound, and then the oxygen can send the electrons down, kicking out the chloride to get to the next step. There we have a great leaving group that the chloride can come in and attack the carbon and kick out the leaving group to give us SO2 gas and chloride ion and our desired product of the benzyl chloride. We can also do this with PBr3, where the oxygen attacks the phosphorus, kicking out of bromine. It attacks the phosphorus because between phosphorus and bromine, The bromine's more electronegative, so the bromine has a partial negative, the phosphorus has a partial positive. So where's the nucleophile going to add? It's going to add to the phosphorus because it's a partial positive. Once it does this, it forms this intermediate that has a positive charge on the oxygen, made a great leaving group, and our bromide ion can come in and displace the great leaving group to give us the alkyl bromide. And all three of those bromides on the phosphorus are open for this transformation to make the alkyl bromide.